Before nano, we had micro technology. With the lots of new innovations in how we could process materials, make things smaller, a new area started developing from this, what is called micro electromechanical systems. Micro electromechanical. So what does it contain? Small size, micro, of course, 10 raised to our minus 6, electro. So if you think about it, what does an electrical system do generally? What do we do achieve with an electrical system? Look around. You have
Send
electric
signals.
send signals. Okay, very good. Look around in your room. What is an electrical system doing?
Give or receive a set of instructions.
Receive, send. That's a computer system, right? Think about electrical system. We have the power switch, switching, right? We have sensors, actuation. So electrical systems do we have a fan, right? Motor. We have a light bulb, light, optical. So there are a bunch of things that happen electrically. What about mechanical systems? Do you see mechanical system? I already gave example of a motor, right? A fan. What else is mechanical? Example of mechanical things.
It could be a fridge or like a dishwasher or something.
With moving fluids, right? We move fluids. We move heat. We have pumps, right? So yeah, you're right, Julio. These are all using pumps or some kind of movement of fluids. So fluids can be liquid, fluid can be air. So when you do those at micro scale, we call it MEMS, right? So that's what the definition is. Is the micro size electronic elements, actuators, sensors, all these things made at micro system. And interestingly, we use these things in almost every gadget that we have. Cell phones, tablets, cameras, gaming devices, your speaker systems, our sensor, movement, motion sensor cameras. You think about it, they all have these miniature things. So this is an example of a micro-sized motor. This is a rotating motor at that scale, micro scale. Now, when we talk about this micro scale system, there's lots of work that has gone behind it. It's not a new phenomenon. It's not something new. It's been, people have been working on these for decades and decades. So we know few things. We know Richard Feynman stock. We know planar fabrication process. Now we have read about these things. So it's a say in 79 is when they created micro machined accelerometer at Stanford. This is very interesting. There are interesting words in it. Micro machined. Like we know machining, lathe machine and all the large scale things, but then you do these at micro scale. In last module, we talked about electron microscopes, right? So we can see these things at micro scale with those machines. We can take image and we can do machining. When you talk about machining, the most important thing in machining is precision. If any of you have ever worked with the lathe machine or done a DIY project, right? What is the most important thing?
The precision is
Precision, measuring, measurement tape, right? If you can't measure things right, you will always end up making a shelf maybe 2 inches too long or 1 inch short or something like that. So that's what we is most important with micro machining. And it says accelerometer. Where do we use accelerometers? Accelerometer. So it's, if you look at this line which is, says 1979, first micro machine accelerometer. Guys, do you use accelerometers anywhere?
in our phones.
Yeah.
In our where?
Phones.
Phones?
Mm-hmm.
phones, cars,
Mm-hmm.
everything that measures your movement. Some people may be wearing Fitbit, some people may be wearing that uh, expensive watch which does same thing that others do, iWatch or whatever, Apple Watch. They all, everything has an accelerometer. It has to be precise, it has to exactly measure. If it doesn't measure your acceleration, then you may be going 40 miles per hour in a 30 miles per hour zone, right? So these are the things. So over years, bunch of uh, measurement equipment came along, like 1982's scanning telling microscope, buckyballs, AFM, carbon nanotubes. So now we are at a stage where we are continuously increasing many more applications of MEMS devices. What we will do is we will read about MEMS and then we will get into BioMEMS. BioMEMS will, that will be my route to get into biology in this module, because ultimately that's what this course is about. How does bio and nano comes together? Because when you get into biology, then we'll start from cell, we go to smaller and smaller things, and we look at some of the things. Important aspect of MEMS is that they can precisely measure phenomena at micro scale and smaller scale, and that phenomena is what we are interested in. At large scale, we can interface human body with things like stethoscope, with X-rays, with things that look at us at tissue level or organ level. With BioNano or BioMEMS, we want to go down at cellular and subcellular level, because many diseases have, now we know they have their origin at that scale. They have their origin at genetic level. They have their origins, maybe a few proteins here and there going bad. Now in COVID, we know there is virus that attacks, gets infects a cell, all nanoscale. How can we measure at that scale? How can we possibly interface that scale and do something to interrupt that cycle of disease, right? Or maybe sense that level of disease. Today, sensing is very important. We go, I guess all of us know, or all of us have got COVID testing done by now, right? Once or twice, or maybe more time, right? How do we do that?
At the nanoscale.
Okay. How do they do the? How do they get the sample?
Well, based on what I've researched thus far, they use
Okay, let me
there's
ask.
there's some.
Have any of us got tested for COVID so far?
Oh yeah, yeah, okay.
Yeah. Right. How do they do it?
They swab you and
They put a stick in, they
yeah,
put a swab in the nose and get the fluid, right?
yeah.
It's a kind of invasive, not very invasive, but it has discomfort to it. Can there be easy way to do that? There would be definitely easy way to do that. How we would do, I don't know. That's what we need to explore. That's what keeps us going in making sensors smaller and smaller. But of course, there are people who are working on how to sense these things and look for these things non-invasively. Here's an example of accelerometer. Some parts are moving, some parts are stationary, some parts are like stuck to the substrate to the lower level, and others are moving. So when the platform, when the whole body moves, the movable parts would stretch, reflex. Whatever there is a kind of a momentum change, we can measure that. We can measure that many ways, by maybe capacitive change, by maybe inductor change, maybe just change in resistance. So here's a like a cartoon of the design of an accelerometer, right? So you have a beam, there are fixed fingers, there are movable mass. So when this mass moves, if you really go close, on the right hand image, what do we see is, so this finger is not, is moving because it's stuck to, it's attached to this part. When say car moves too fast in this direction, these things are gonna draw a little bit backward because the whole platform is moving faster in that direction, right? So now these two wires, these two kind of micro beams, they have kind of a capacitance in between them. If that changes up and down, capacitance would change, right? Simple concept behind that. It may be in an inductor, it may be resistors uh, measurement as well. But that becomes part of a big circuit and we can get a chip of accelerometer, right? Has anybody ever used an accelerometer chip, accelerometer module? I know there is a senior design team that's using one. So basically they're trying to figure out if a bike rider can hit something. So which would mean sudden change in acceleration, right? That's an accident, kind of identifying. So these are cheap. You can buy one module for like $15, right? So there's, it says there's a story, it's a triple axis MEMS accelerometer, low noise, power consumption, and whole spec sheet will have a bunch of detail about it. MEMS. Can somebody tell me what does MEMS stand for?
Uh, I just wrote it right now. Microelectronic. No.
Motion sensor.
Yeah. There, yeah.
Motion sensor? Dude, I walked you through microscale, electro, mechanical.
System, right?
So
Mechanical
that's,
system.
yeah,
Micro electro
electromechanical system.
systems. Yeah.
So how do we make them? Some maybe just we take a large thing and we start making smaller version of it. We call top down, right? Or we start bottom up. We say, okay, let's look at some phenomena at micro scale and build something around that. Right? So there are different ways how they're made. If they're too small or their signal is too small, we make bunch of them and put them together. Right? Here is an example of what many of us may be using. Do you have a projector at home? Have you used a projector
Yeah.
in classroom and places?
Hmm.
There is a thing written on these modern projectors. It says DLP. Have you ever heard the word DLP? It's a Texas Instrument chip. It's called DLP. It stands for, I think, Digital Light Projection, DLP. DLP technology. What it did was it dramatically changed how projectors were done or things were projected. What it has is bunch of mirrors in it, micro mirrors. This is what is shown right here. Micro mirror array. Each of this white dot thing is a very shiny mirror. What does it do? Light, it projects on it, it would reflect whatever color it's supposed to reflect. So you are controlling the reflected light behind it. And what we end up getting is very high resolution pictures. High resolution pictures with achieved with millions of pixels, right? That's the whole idea. So we apply magnetic field to it and we adjust the mirror in it, which gives us different colors and different precision. So much so now we have these DLP projectors that you can put in a pocket, get to a conference room, put it out and start your presentation. You don't have to carry that whole big thing that used to be. How expensive they are? $90. Can you believe that? That's MEMS technology. That's you and me, electrical engineers who have enabled that. That's what Silicon Valley is doing, right? Now, not just Silicon Valley. This is Texas Instrument. This is Dallas, right up the alley. Why? MEMS, making things at micro scale. And it's not just projection, or there are a bunch of applications. There are moving vehicles. There are vehicles which are uh, aircrafts, ships, boats, space applications. Talk about oil exploration. These things, you know what are these called? The floating platforms in sea, which are drilling oil. They're constantly moving, right? Sea. So they're measuring their movement with accelerometers, their gyroscopes. Gyroscope is a thing we use to find magnetic norths. It gives us exactly where we are located in space. So imaging, uh, biosensing, whole bunch of things. You know, before there was Google Glass. I don't know if you, any of you remember Google Glass thing. Google started a project, I think 10 years ago, something like that,
Yeah, what
where they
happened to
put,
that thing? I never saw development after like they
yeah,
published the beta, and then
people
after that it just disappeared. Or I never heard of it. Like what happened after?
people didn't accept it. We don't want our privacy to be invaded,
Yeah, too much invasion of
right?
privacy. I'm assuming. Yeah.
Yeah. The thing is, if I'm taking your picture, I have to take steps. I have to put my cell phone up so you know I'm taking your picture or I'm taking a picture somewhere. But I don't want this to be like you come to my office and you have this camera and you are taking my pictures. I know I'm not that famous, but still I don't want my pictures to be taken without my consent. I'm just giving an example. So people were wearing them, and they came up with yeah, people were calling them really nasty names of that
So, Dr. Igbo,
technology.
what do you think will happen with the new Neuralink from um, what's his name?
Elon.
Yeah, from Elon Musk. What do you think is going to happen with that?
So he he talks about lots of things. He talks those, yeah. There are visionaries, but problem sometimes is that public is not ready to adopt them. So yes, on technological side, it may happen. It may very well become a reality.
Yeah,
I
but
think
But
he's smart about it because the way he's approaching it is he's not gonna be releasing it like this. He said that he first is gonna use Neuralink to cure problems in the brain. It's gonna be like medical, and then
yeah,
like 10 to 30 years in the future, it will
right.
slowly increase to become of what you're suggesting, where like oh it's
Yeah.
gonna be in your brain and things like that.
So it's social acceptance and cost as well. It's a very interesting example I give sometimes. You know, cochlear implant, people have this in the deaf people, right? So those who cannot hear, they have this implant which directly gets a cable to the nerve, cochlear nerve. You know who were the most resistant to that technology? It was good technology available, free of errors, everything. Deaf community itself did not want that because having cochlear implant meant uh, loss of the that culture, right? And sign language culture, a community where people come together and they can communicate with each other. It's interesting. Look up what were that. So the deaf mute community, they were the major. They were very slow in adopting cochlear implants. So making a technology does not mean it will become people will accept it. So there, and I know for more than 15 years, I know folks who have been working on making on putting cameras and sensors on contact lenses. But it's interesting that yes, there it's technically feasible. There have been reports where they have shown it works, but big question is if people would want to put that metal strip in their eye, right? So we as human may not be ready. But this is again micro scale innovation, MEMS, lot of MEMS things that go into that. There's and we can talk about more things, but just wanted to introduce and see show you where MEMS and BioMEMS come together, and then we'll continue this discussion. Lots of moving parts at micro scale. Chains, micro drive, right? Micro chain drive, where chain is going across around gear, right? Think about your bicycle and think about a micro bicycle as well. Edgar has the backdrop picture of bionic arms here. See, so bionic arms, bionic limbs, they are using lots of MEMS devices in them. It's not just future is not just in devices. There's medicine, there is exploration, there is ecological application, there's usage of sensors, what you call part of IoT, Internet of Things, where any gadget, any device can be controlled, accessed, interfaced from anywhere through multiple channels, not just Bluetooth or Wi-Fi. They can be devices talking to each other and connected to a gateway in a house. So this is part of making MEMS, making smaller and smaller chips. Now, we use the same procedures, same ideas that we talked about nanofabrication. We make patterns, we grow oxide, we remove material, we add different materials, metals, semiconductors, a whole bunch of things, same concept, same processing steps involved. But it is you and I who would make a recipe on our design where we would say, okay, I want to first, for example, on the right-hand side picture, it says, first I put a sacrificial layer, I pattern resist, I remove it. So we decide how we want to do and what we want to achieve. Now, as I was saying, we want to go down smaller than the scale of organ or tissue. We want to look at individual cells or small organs or small parts of it. For example, this is an eye of a fly, Drosophila. This is a very commonly researched fly because it has lots of genes that match human. It's interesting. Look at that Drosophila. So this is its eye shown in an electron microscope. And on the right-hand side is, can you guess what it's written? It's red blood cell, 8 micrometer, right? So when you look at these cells, when you look at these things, we see an opportunity that we can interface individual cells. In many places, they come up with different terminologies over the years. It used to be called SCA, single cell analysis. So MEMS has then gone into many directions where we have movement, not just movement, we are measuring. I start from the top. We are probing at microscale. We have optical devices at microscale. We are measuring forces, pressure, sound, inertia, magnetic fields. We have radio frequency devices that communicate, RF MEMS. So these are, for example, the soldiers, they wear night vision goggles. They have MEMS devices, they call bolometers, that can detect uh, that specific range of light, which I cannot see in the dark. So these are all MEMS devices. Microscale actuation motion, BioMEMS. BioMEMS are microfluidic, which is much more important for what we're going to discuss. I don't see Luis Amaro and Julio. The videos are off. So going from MEMS, then we say there are from micro and nano fabrication, we go and we bring chemistry from the other side, knowledge of microbiology and chemistry from the other side. And what can we do at the interface? We can engineer systems to look at life, engineer systems to look at living things. And this is where the knowledge of materials and interfaces that comes in. What we achieve with that, we characterize and find the behavior of living things at that scale. All right? So far, so good? Okay. I want to get into a little bit basics of cells, biological molecules, characterization technology. Okay.